we'll jump right in with the SN1 reaction. SN1 stands for, the S is substitution, which I'll write as sub. The N is a nucleophilic, and the 1, well, that's where everybody gets confused, so let's break it down. The 1 tells us that it is unimolecular, which specifically means not one-step reaction, but rather one molecule reacting at a time. This is really, really important to recognize. Unimolecular is actually a reaction with many, many steps. Depending on the specific reaction, you can have 3 or even 4 steps. And the reason this has so many steps, or just going back to the unimolecular concept, what this means is it's a reaction that happens one step, one molecule at a time. And this is a slow, slow, slow reaction. When we talked about SN2 and E2, we talked about how there were fast reactions with strong attackers that happen in one step. This one takes its time, and you have one thing happening and another thing happening, and it goes very, very slow. So let's look at a straightforward but kind of tricky reaction that professors like to throw at you. And that way we can look at all the different pieces. We'll start with the molecule that we were using for SN2 and E2, because yes, it can undergo SN1 and E1 as well. What I have here is my alpha carbon, the carbon holding the leaving group, that is very partially positive. And the reason this is partially positive is that bromine, being a highly electronegative atom, is pulling and pulling and pulling on the electron density between itself and carbon. In a strong reaction, it gets kicked out. But if nothing is coming to kick it out right now, then as it pulls and pulls and pulls, eventually it will completely break off, taking those bonding electrons with itself, so that you get something in solution that looks like this. We have a bromine with the 3 lone pairs that it had to begin with, and now we'll show these 2 electrons in light blue as the extra lone pair it grabbed when it broke away from carbon. And it's off somewhere in solution, never to be seen from or heard from again, minding its own business. What we have left from the molecule, though, from the starting molecule, is a carbon that now has a deficiency at the alpha carbon. Where the bromine broke away, we have an incomplete octet, which gives carbon a formal charge of +1. This is really important because if you look at the starting molecule here, the carbon holding the leaving group is sp3. It is chiral. It has stereochemistry, and the chirality is whatever we started with. But what we're left with for this first intermediate is a carbon that is sp2. What is the shape of something that is sp2 hybridized? If you signed up to receive live notes before, do you need to sign up again? Yes, because then I'll have you tagged for this one. If you signed up in the past, I had you tagged for the other one. My professor also mentioned this last semester as well. That's good that your professor brought it up because a lot of students don't. So with an sp2 hybridized carbon, it is trigonal planar and flat. That means it no longer has any stereochemistry. And for the next step, if I have a nucleophile come in and attack, it can happen from the top or the bottom. So let's look at the nucleophile really quick. If I'm looking at a molecule that is a nucleophile, it comes from the word nucleo, which is nucleus, and phile, which is loving. A molecule that loves the nucleus, if the nucleus is positive, this molecule will be negative or partially negative. In a strong reaction like SN2 or E2, it does a quick attack. In this case, it wasn't strong enough to kick out the bromine. And so the carbocation formed, that means there's something weak in solution waiting. It's not strong enough to attack, but it is waiting for an opportunity when something is so obviously receptive that it will attack. And often you'll see something like this, where you have H2SO4 with nothing else given. H2SO4 is not an attacker. Professors love to trick you with this. What we're looking at when you see H2SO4 in solution is an H2SO4 dissolved in water. Water was not given, but it is implied because H2SO4 has to be in some kind of solvent. Not only that, but H2SO4 being a very strong acid will dissociate to give me an H plus and an HSO4 minus in solution. HSO4 minus is a spectator. It's not reactive. It is not strong enough to do anything. I know some professors will show the HSO4 doing an attack. It cannot. It is too weak. The H plus, though, is not floating around by itself. What happens is when you put a strong acid into solution, the solution itself, in this case, a molecule of water, will pick it up and give me the hydronium ion, H3O plus. So if you see H2SO4, what you need to take away from all this, ignore that. The takeaway is that you have a source of protons in solution, which you can write as an H plus or as an H3O plus, and they imply the same thing. H plus being held by a molecule of water. You are so very welcome. Thank you for subscribing. And for everyone else, if you haven't subscribed yet, please, please, please subscribe. I'm looking forward to reaching 1 million subscribers very soon, and I need your help. So please, please hit that subscribe button. Looking at this reaction, the H plus or H3O plus is not a nucleophile. We said the nucleophile is nucleus loving, positive seeking. A positive is not going to attack a positive. It has to be something negative or partially negative. So what are we going to use? There's no other chemical, no other reagent given. When you have nothing else, you use the solution itself. If the solution itself can be used, this is called a solvolysis reaction. Comes from the word solvolysis. The solvent is going to break apart. The solvent is participating. The solvent does the attack. And so I bring in a molecule of water, which is the most negative thing that I have in my acidic solution. And that's because I have these lone electron pairs that are highly electronegative. The solvent will reach out and attack at the carbocation. Let's kind of sneak over to the right because I have too many notes here. I'm running out of space. So what I have now is a new bond. Let's change the color so that we can see where the bond is coming from. We'll make this the green electrons attacking. So these green electrons now form a bond between carbon and the water molecule. But here's what we have. If the water molecule had an oxygen with 2 lone pairs, one of them did the attack. The second one is still there. Oxygen now has 3 bonds, 1 lone pair, and therefore a positive charge. This is an oxonium cation. It is a positive intermediate, and therefore this is not the final step of my reaction. I do need some space. So you move down, please, and thank you. There we go. All right, so what will happen next is we have to deprotonate that positive molecule so that we can have something neutral. And the best way to do that is to just find another water molecule in solution, grab that proton, give oxygen back its electrons, and now look at what I have. My starting molecule, a green bond to the oxygen, and then 1 hydrogen remains, 1 lone pair that we had, another lone pair that we get back from these electrons here. This thing is neutral. This is also chiral, let's not forget. And then somewhere in the solution, we have an H3O plus from the purple water molecule that grabbed the light blue hydrogen, and that's just the catalyst reforming in solution. This is chiral. What is the relationship between the starting chiral molecule that we had and the ending chirality of our substitution product? Questions in the meantime? From what I know about SN2, E2, SN1 and E1, SN2 have a strong nucleophile, E2 have a strong base. Yeah, okay, SN1 weak nucleophile, E1 a weak base. Luna, that is the best summary ever, because if you can understand that difference, you will understand how they react. So that is absolutely perfect. Follow-up question. Does that mean that SN2 and SN1 reactions can form with a base and vice versa? Yes and no. A molecule can act as a base or a nucleophile. It simply depends on the context of the situation. I showed you water acting as a nucleophile here, but in the next reaction, I'll show you water acting as a base. And so it's not that a base can't do this and a nucleophile can't do that. If it's reacting as a base, we call it a base. If that same molecule does the work of a nucleophile, we call it a nucleophile. Back to the stereochemistry. Because we had a carbocation intermediate, the fact that this one was on a wedge has no bearing on the final product because the flat intermediate, why did that happen? Because the intermediate is flat and trigonal planar, the water molecule can come, why does it keep doing that? The water molecule can come and attack from the top or the bottom. And that means when the product is chiral, the product is racemic. We have 50% R and 50% S because of that carbocation intermediate. So yes, it can attack from the top and the bottom. Here I showed it coming from the side, but technically it's a top or a bottom attack, and the product is racemic. So let's take a look at some of the different things that came up in this SN1 reaction so you can have some key takeaways. The first is the fact that we had a carbocation intermediate. This right here, this is the slow step, or technically this right here. Slow step. Carbocation formation is not very stable. Yes, we talk about a stable carbocation where if it's tertiary, it's more stable than secondary, more stable than primary, all that good stuff. So let me write it off for you. A tertiary carbocation is more stable than a secondary carbocation, which is way more stable than a primary carbocation, and that is more stable than a methyl carbocation. You will not see these forming at the substitution elimination reactions. We're looking at tertiary and secondary because this right here is the most stable. But it's not that it's very, very stable. It's most stable compared to the other ones. Because a carbocation is not very stable, the carbocation formation is the rate determining step. And that makes it a very, very, very slow step. However long it takes to form the carbocation, that is how long it takes to do the entire reaction. Because the moment that carbocation forms, everything else immediately reacts so much faster that it's like looking at something that takes 10 years and then the next part takes 2 seconds. So very, very slow carbocation. Everything else is much faster. And because of that, if we're looking at the rate of an SN1 reaction, we're simply looking at some constant K times the carbocation formation. So it's the concentration of the alkyl halide, the molecule that has the leaving group on it, where the leaving group leaves and forms the carbocation. Nothing else is going to impact the rate of this reaction because everything else is very, very fast by comparison. This carbocation is a crucial intermediate. And here is something really important. Carbocation must take place in an SN1 E1 reaction. Never, ever show me a carbocation in SN2 and E2, only SN1 and E1. Some notes on this reaction. We started with a molecule that looked like this, and I showed you the product very quickly. So let's actually look at the shortcut of how to come up with a product. What you do, as soon as you recognize that you have an SN1 reaction, let me rewrite it, H2SO4. We said this is a source of H+ in solution. That is not your nucleophile. We did not have a solvent given, but we recognize the solvent. Solvolysis. We recognize that water is implied with sulfuric acid. This is a solvolysis reaction where the solvent itself is the weak nucleophile. And as soon as we recognize it'll be an SN1 reaction, you redraw your carbon skeleton as you see it. You cross out your leaving group, and in its place, you put whatever you have as the solvolysis solvent minus 1 proton. So let me redraw it like this. We take off 1 proton because that'll be deprotonated in the final step, and then you add this. I can add it on a wedge as an OH, but I also have to show my second one because remember, this can do a racemic mixture if it's chiral. So that is another key here for the SN1 reaction. In terms of speed, because the carbocation is the rate determining step, the more substituted the carbon holding the leaving group, the faster that reaction is going to take place because the faster the more stable intermediate wants to form faster. The solvent for this reaction is something that is polar and protic. And the reason we're looking at polar and protic is we want something that will stabilize the charges. If we have all those charged intermediates, we want it to be surrounded by opposite charge so that it can be stable, so that it is likely to form. A polar protic solvent, polar means that even though they have covalent bonds, they're not equal, they're not exactly the same electronegativity. One side is going to pull a little more than the other, giving us partial charges. I show you water in this case, so let's take a look at the water molecule. The bond between oxygen and hydrogen is covalent, it is sharing, but oxygen being highly electronegative has, whoops, that's not positive, has more negativity. That makes both hydrogen atoms very partially positive. If I give you something like ammonia, the same thing happens. We have a partially negative nitrogen and 3 partially positive hydrogen. This also works for alcohol. I'm going to need some room here. Here we go. If I have an alcohol, then say this is a CH3 bound to an O, bound to an H. The portion of the alcohol that looks like this portion of water, this portion of ammonia, they all behave exactly the same. Partially negative, partially positive, and that's what makes them a good solvent. Now, what is going to determine if the reaction will be between an SN1 or an E1 in a situation like this? I gave you SN1, but did it have to be an SN1? April 7th. Wow, that is a difficult exam just around the corner. I wish you all the best with it. Can other strong acids be used also? Yes, any strong acid is going to work here. And typically you're given H2SO4, but you may see HCl, HNO3, what else have I seen? H3PO4. Anything that looks like a strong acid is probably reacting the same way. Would it be possible for the solvent to be nonpolar? If this is the case, does it mean there is no reaction? It wouldn't dissolve and it wouldn't stabilize the carbocations. For example, if you put it into benzene or toluene, you're not going to see an SN1 reaction. Now, I showed you this as an SN1, but the thing about SN1 and E1 is they are always competing. They're always in competition. And that means if an SN1 reaction takes place, very, very likely scenario is that an E1 reaction will also take place. Hello, Brian. Do you mind repeating why you wanted a difference in electronegativity when working with a solvent? That is a very good question, Hannah. When you're looking at a solvent, you're looking at how it's going to interact or not interact with the molecule. And in the case of our reaction, we have, let's go back to the very first step. This is a really, really important question because why, even though bromine is highly electronegative, why would it want to break away? When bromine breaks away, you're creating 2 very unstable situations. Situation number 1, carbocation. Situation number 2, Br-. Charge is a burden, and molecules do not want to hold a burden if they don't have to. So what makes it possible that these burdens will still form? If I put this into a molecule of water, then the partially negative, the partially negative oxygen of the water molecule is going to surround that carbocation. And when it does so, that positive charge is stabilized. There's moral support around it. They're holding a little bit of negativity here, a little bit of negativity, a little bit of negativity. And because it's surrounded, it's stable. The Br-, same thing. If I surround it by the partially positive hydrogen of the water molecule, it's stabilized. And therefore, it doesn't mind the fact that it's holding a negative charge. This is what it's like saying to someone, come on out to this event we're having, and just bribe them with something that'll make them feel comfortable. We have your favorite food, your favorite drink, your other best friend is there, just something that will make it so happy that it's worth enduring this thing that it doesn't necessarily want to do. Do you have stuff on resonance? For other topics, email me and I will be happy to point you in that direction. Why are beta and alpha hydrogen, carbon important in these reactions? So in the SN1 reaction, we're only looking at alpha. And in this case, the alpha carbon is the one that holds the leaving group. That is the one that will undergo the attack. When we look at the E1 reaction, we're going to see that the beta is also something that plays a big role. So let's actually look at an E1 reaction. And just to confuse you, we're going to start with the same exact molecule with a bromine sitting on the secondary carbon. And to make it more exciting, we're going to use the same situation again, H2SO4. Okay, I showed you this as an SN1 reaction. Watch how this can happen as an E1 reaction as well. There is nothing strong going on here. Nothing is going to kick out bromine. And so bromine is pulling and pulling and pulling. And eventually it breaks away, giving me a carbocation and a Br- in solution. But I just realized to jump ahead and I did not fully and properly introduce the E1 reaction. So let's hold that thought and talk about what the E1 reaction is before we see it happening. The E1 reaction should really be a beta E1 because it's a beta E for elimination. And the 1, once again, stands for unimolecular, telling us that is one molecule reacting at a time, potentially multiple steps. Let's look back at the mechanism. Where did I show you that mechanism? Hang on. Here we go. Okay. So we had 1 step, 2 step, 3 step. This was a 3-step reaction. Let's look at what happens with this one. Unimolecular, once again, means it's one at a time. Multi-step reaction, because it has the carbocation intermediate. And the key, of course, is, like I just said, a carbocation. Make sure you connect your one-type reactions with the carbocations. SN1, carbocation. E1, carbocation. SN2, nope. E2, nope. So we have a beta elimination. What is beta? That is also really, really important to understand. So let's look at a carbon holding a leaving group. We'll just put Lg for leaving group. The carbon holding the leaving group, my alkyl halide, that right there is my alpha carbon. The carbon directly attached to that, that's my beta. That's my beta. The next one is gamma, delta, and we don't care. We only care about alpha and beta. In an SN1 reaction, we only dealt with the alpha carbon. In an E1 reaction, now that we know what we're looking at, this carbocation is positive and very much susceptible to attack. But if nothing attacks it right away, then the positive charge is going to be stabilized by the remainder of the molecule. If I have hydrogen atoms over here, some of that negativity from the bond is being pulled towards that carbocation. If I have hydrogen atoms over here, some of the bond negativity is being pulled towards that carbocation. So they stabilize the carbocation. In the process, these beta hydrogens are becoming very partially positive. And this is what drives the reaction. Because if I have a partially positive hydrogen here, and a water molecule is moving around the solution, minding its own business, and it sees a hydrogen, it could attack here, but the hydrogen is closer. So it's just going to grab that hydrogen, give the carbon back its electrons, and that gives me a molecule that looks like this, with a pi bond now between the alpha and this beta carbon for my E1 product. But if I had a different water molecule floating around the solution, and this water molecule decided that it's going to grab the orange beta hydrogen from the other side, giving it back its electrons, that would give me a different pi bond. That would give me a pi bond sitting right here between the terminal alpha and beta for a completely different product. 1 butene versus 2 butene. And if this molecule that has sp3 bonds and therefore free rotation decided to rotate before I got attacked, then I could have gotten yet another pi bond at the secondary position right here for a total of 3 products for my E1 reaction. So which one is the major product and which one is the minor? If you're joining late, welcome. Don't worry about taking all the notes. I am taking them for you. Just type live notes in the comments and I will email it to you after. Yes, even if you're watching the recording. Let's see. If SN1 and E1 are competing, ask me this question because we're going to ask me again soon because we're going to cover that. When you discuss SN2, I did not. That's a good question. Ask me at the end and maybe I'll have time to cover it. What is the best way to differentiate between which reaction is forming? So Luna, that is a whole other topic in itself. I have an old session on it called Choosing Between SN1, SN2, E1, and E2. Make sure you go watch that. And maybe we could do another session on that soon. How do you form mechanisms for the product of these when they react with the solvents or other alkyl halides? I'm not sure I understand your question. So in this case, the solvent is the attacker. But do you mean one of these molecules attacking another one of these molecules? Because if that's the case, that's not going to, if that's what you're asking, then that's not going to happen here. In SN1, is there a partial inversion when the leaving group hovers? Technically, yes, but I want to say 98% of my students don't learn that, so I don't bring it up. How do you know which side the beta hydrogen is on? Is beta elimination always a hydrogen? Yes. So let's look at the molecule in more detail. This is what we had initially, and we had a bromine sitting on here on a wedge. There was also a hydrogen here on dashes, but we don't care about that. This is my alpha, this is my beta, this is my beta. I have 3 hydrogens here. Any of them were susceptible to attack. Not 3 hydrogens, what am I talking about? That would have 5 bonds, only 2. This one over here has 3, and again, any and all of them were susceptible to attack. I also have hydrogen here, but I don't care about them because these are gamma. They're too far away, and therefore they're irrelevant. Every single beta hydrogen is partially positive as soon as this is gone and the carbocation forms. So all of their electron density is being pulled slightly in that direction. And then it's simply a question of which one do I happen to pull off. They're all susceptible to be pulled. The question is really about why you would pull one over the other, depending on stability. And so this is where we have to look back at Zaitsev's rule. Zaitsev's rule tells us that the more substituted the pi bond, the greater the stability. And so if I have a more substituted pi bond, then that's the one I'd be going for. So we'll start with this one right here, no substitution. This is a mono substituted. Di-substituted, I can have 3, most stable, second most stable, third most stable, tri-substituted, and tetra-substituted. So let me show you the highlighter trick that I used to figure this out. Highlight your pi bond. I'm just going to highlight them all real quick. And then what you want to do is draw an arrow coming out of the pi bond. One arrow makes this mono sub. 1, 2, 1, 2, 1, 2. These are all di-substituted. 1, 2, 3, tri-substituted. And 1, 2, 3, 4, tetra-substituted. The tetra-substituted is going to be your most stable. The one that's not substituted is the least stable. And so when you're trying to figure out which one is the major product, always go for the more stable of them all. With the di-substituted, the one that's most stable has the 2 R groups furthest away from each other, as you see here, versus here they're close together, here they're closer together. And so if we look at the 3 products that I gave you here, this one is your major product because it's di-substituted trans. This one is your minor product because it's mono-substituted, and this one is in the middle because it's di-substituted cis. So trans, most stable, cis, slightly less stable. I forgot who asked the question. Navy, was that you? And if yes, does that answer your question? Do alpha beta carbons change with ketones? Yes. So with ketones, you count it differently because the carbonyl carbon is like your 0 and the one next to it is the alpha. Lola, yes, let's actually look at that next because that's really important. Question. Our lecturer asks us to react tert butyl bromide with water, give the product, and then asks us to say what reaction it was. So let's take a look, because that is actually a very good question. Tert butyl bromide with water. So we start with a molecule that looks like this, with a bromine leaving group. This right here is achiral, so it doesn't matter if I draw it on a dash or a wedge, because carbon has 3 R groups that are all the same. If we react it in water, we need some kind of catalyst. So let's assume that your reaction also gave you H2SO4, which I don't see in your comment, but let's assume it was there. And then we'll come up with a mechanism and everything. First thing to recognize is that H2SO4 is an H+, a source of ions in solution, but it is not an attacker. Water will be the attacker. Water is very weak, and therefore it's not able to kick anything out. It has to wait and wait and wait until eventually bromine leaves, and you're left with a tertiary stable carbocation in solution. At this point, the carbocation, that was the slow step, it finally formed. I have a water molecule that can come in for the attack, and the question is which attack will happen. I can attack in more than one position. Because each R group here, each beta carbon is the same exact one with 3 hydrogens, it doesn't matter which one I choose because they're all exactly the same. So for reaction 1, I will show the water molecule coming in and attacking directly at the carbocation, giving me product number 1, where I have the water forms right here, 2 hydrogens, 1 lone pair positive charge. I'm going to show minus H, I don't know why I put a 2 there, minus H plus to make it deprotonated. And this way I can just jump ahead to the next step. I know you're asked for the mechanism, so you just show, you know what, let me show the mechanism since I said I was going to do that. Disregard that. What I have is my first intermediate, which is a molecule that looks like this with an O, an H, another H, 1 lone pair and a positive charge. So we'll bring another water molecule from solution, grab a proton, give it back the electrons, and that'll be the first product in this reaction, which is an alcohol as the SN1 product. How do I know it's SN1? SN1 is substitution, and I substituted bromine with an alcohol. For this second mechanism that I can do, I will show my water molecule coming in, but instead of attacking at the carbocation position, it's going to grab one of the beta hydrogens and give the carbon back its electrons. That will give me a molecule that looks like this, but now with a pi bond between the alpha and the beta. Because this molecule is fully symmetrical, this is the only option. And this right here is the product of E1. So I have 2 products for this reaction because they are always in competition. Annika, let me know if this makes sense, if this is what you were asking, and hopefully this helped clarify that, yes, they can absolutely be in competition. So how do you know when to choose one over the other? Typically, they're all going to be E1 and SN1. The difference is that anytime you see heat, heat is going to help all the reactions, but it tends to favor elimination over substitution. Typically in a 2-type reaction, E2 is favored over SN2. With E1 and SN1, heat will still favor both of them, but maybe favor E1 slightly more. So it's not a blanket rule. Heat E1, they're both going to happen faster. E1 will happen just a little bit more. Excellent. I thought E1 would only happen with heat. No, so they're all very, very slow. It's just a little bit less slow with heat. These are very slow reactions. These are not ideal reactions, but it is a little bit less slow, meaning slightly faster if you add in some heat. So let's go back to where we were talking about these reactions. A couple of takeaways for the E1 reaction. Just like with SN1, the rate of an E1 reaction is equal to some constant K specific to the reaction times the concentration of the alkyl halide, the molecule holding the leaving group. What you're looking for in an E1 reaction is an absolutely carbocation intermediate. You cannot have E1 without carbocation. It is a slow reaction because it has a carbocation. It follows Zaitsev's rule. Zaitsev's rule tells us that the most stable carbocation, the most stable pi bond is going to form. This right here is the Zaitsev product. If you have a reaction, typically with E2, that forms the least stable, that will be the Hoffman product. But in an E1 reaction, we're following Zaitsev's rule. SN1 and E1 are going to be in competition. I don't know why I did that. We absolutely can do solvolysis. That means the solvent is participating in the reaction. So we need a polar protic solvent. And yes, heat helps. It is not the end all be all, but it does help. This triangle, that's a delta symbol. That simply means that I'm adding heat into the system. If you have questions on the E1 reaction, let me know. If not, let's try something exciting. Can you explain the first step to an E1? Yes, the first step in both an SN1 and an E1 reaction is the carbocation formation. So what we showed over here is that bromine is a highly electronegative atom. And even though it has a stable bond between carbon and itself, even though they're sharing their electrons, full octets, everything should be happy. Fact of the matter is, bromine is electronegative. It is greedy. It is pulling on the electron density between itself and carbon and eventually breaks away, forming a carbocation. That is the first step and the rate determining step. Will E1 reaction have a higher activation energy compared to SN1? Yes, very similar to what we looked at in the SN2 and E2 session. I am going to make up the numbers here because I don't know them, but I'll show you the general idea, the general relationship between them. What we're looking at here is a graph of energy, an energy diagram taking place over time. If I start with a molecule, my alkyl halide, it has some kind of energy at this level. If I undergo an SN1 reaction, I will have my activation. It goes a little bit lower. Typically, we have deprotonation, so that could be 2 steps. SN1, the last one we did was 2 steps. So let me see. Leaving group leaves, we attack 2 intermediates. So this one, the leaving group leaves, we have a carbocation, gets attacked. There should be a third one. Hang on. So we'll show 1, 2, 3. That could be the product of an SN1 reaction. And as you can see, it's a lot lower in energy than the starting molecule. It is a lot more stable. But if I take this same situation and I put in a higher activation energy, I can get something a little bit lower. So you see how the cost, I don't want it to perfectly overlap. Let's go like that. There we go. The cost, the activation energy is higher, but the product is more stable because it's lower in energy. And for SN1, you have an activation energy, another activation energy, another activation energy, because if you look back at the mechanism, we had multiple steps: carbocation formation, water attacks, deprotonation. And so there could be multiple steps. 1, 2, 3 for this reaction. Who asked the question? Lola, does that make sense? And does that answer your question? So without heat, is SN1 the major product? No. So they can both happen, but if you put heat into the system, then a lot more will go the elimination route. If I'm given a question like that, should I show both SN1 and E1? Yes, unless your professor is the type who specifically says heat E1 incorrectly, but if that's what they say, that's the product you want to give. Otherwise, make sure that you show both of them. Will E1 have intermediates? No, because E1 has a carbocation formation. That's, well, technically, yes, there's one intermediate, the carbocation, and that's it. Oh, wow. That's a good point. So E1 should not look like that. E1 should have 2 bonds. The first one is the why is that not working? The first one is the carbocation formation, which will be exactly the same because that's the carbocation intermediate. The second one, and again, I'm making up these values because I don't know the numbers off the top of my head, but the second one will be higher. There we go. Good question, because yes, the carbocation is an intermediate for both of them. This right here is the transition state. So this is when you have the R kind of almost broken away from the X, partial negative, partial positive. But this is the full-on stable carbocation intermediate. As you can see, it's more stable than the... It's not more stable on the starting molecule. Okay, my graph is completely not drawn to scale, and I don't feel like changing this whole thing. So let's just show that this started out lower. I wonder how I can reset that. Oh, there we go. Okay, managed to fix it. Yeah, like I said, I made up these numbers. And the idea here is that an Rx is more stable than a carbocation. A carbocation should probably be like this energy level. So don't quote me on my numbers. Clearly, I don't have them memorized. So yes, E1 will also have intermediates. One very common E1 reaction that you're going to see with an extra intermediate is using something like this. Say I have an alcohol and I react it with H2SO4 and heat. That is all I'm given. This right here will be expected as an E1 reaction. Your professor does not want to see SN1. They want to see E1. But wait a minute. You just said that they will be in competition. So why is this only an E1 and not an SN1 reaction? It's a trick question. But question mark emojis in the comments if you don't know. It's not an exception to the rule that you have to memorize, but it's a very, very specific reaction. First thing happens in an SN1 or an E1 reaction. Let's first confirm that this will happen via SN1 or E1 reaction. And I'm doing a couple of practice problems with you right now, but if you need more practice on this topic, I have a complete substitution elimination midterm from complete the reaction, figure out if it's SN1 or SN2 or E1 or E2. Quite a few pages of problems. Just put midterm in the comments and I will give you a link to download it for free and you can practice. So back to this question. How do we know that it's going in the direction of an SN1 or E1? I'm looking at what it is that I have here available to react. I have an H2SO4, which is a source of protons in solution. I see no nucleophile, no base, no attacker, no solvent, nothing. A lot of it is implied though. H2SO4 is an acid catalyst. It implies that I have an H2O as my solvent, which, oh yeah, that could be my solvolysis reaction. H2O is weak, so it would go SN1 or E1. Let's hold that thought. The problem is the first step is a carbocation formation, but I absolutely cannot have an OH leave. OH would form an OH minus leaving group. That is a strong base, strong nucleophile, will not happen. So if I have a bad leaving group, something that does not want to leave, the first thing I have to do is bribe it. And that is where that H plus catalyst comes in. The alcohol will grab the H plus from solution so that what was an OH is now an OH2 lone pair positive charge. I just turned what was a bad leaving group into a good leaving group. And what does a good leaving group do? It leaves and stays gone. Or as my son likes to say, it go gone. So we make it go gone, as my kiddo says. And that gives us a carbocation intermediate, where the carbocation is susceptible to attack by the solvent, and the beta hydrogens are also susceptible to attack. So I have light green beta hydrogens here. We'll put some light blue beta hydrogens over here. Now, here is why this will only do an SN1, an E1 and not an SN1. What product do I get if I have an SN1 reaction? If a water molecule comes and attacks right here, won't I get an OH lone pair positive charge? Yes, I will. Where have we seen that before? We have seen it right here. If water attacks, all we're doing is reversing and getting an alcohol again. So technically, there is no reaction. If I react a molecule to get the same exact molecule, that was no reaction. And so we won't show that. What we will show, however, is the water molecule grabbing one of the protons to give me an elimination reaction. And if I'm looking for just the most substituted product, the Zaitsev product, this is what I'm getting. That is why H2SO4 and heat with an alcohol is an E1 reaction. Specifically, this is a dehydration reaction. Dehydration, we remove water. What is the water that we remove? H and OH, H2O. That is the dehydration E1 reaction. How did I know that this is the hydrogen to grab to get the most substituted product? I know that this is the most stable based on Zaitsev's rule because we had already analyzed it here, but that's because we had taken the time to figure this out before. What if I didn't have time to draw them all and I didn't want to waste time coming up with all the products only to find the major? Here's the trick. If you grab a hydrogen from the most substituted carbon, you're going to get the most substituted pi bond. Grabbing a secondary beta hydrogen is going to give me a more stable, more substituted pi bond than grabbing a primary. And so looking at the beta hydrogen, seeing this beta is secondary and this beta is primary, if I grab this secondary, I get the major product. Whoops, seem to have lost half the product. There we go. That is how I quickly get the major product. Question. Do you mind how to differentiate between a good or bad leaving group? My professor only provided a list of examples rather than explaining the reasoning. Brianna, if you don't understand the reasoning, how are you supposed to know it? Because if you memorize, it's just a whole lot of things to memorize, and that is very, very not helpful. So let's take a look at what makes a good leaving group, because without a good leaving group, we cannot kick it out. A good leaving group is defined by something that will leave and stay gone. It leaves and stays gone. So what makes something stay gone? If it is stable in solution as is, it has no desire to come back. So let's look at a couple of different molecules. If I have a bromine and it leaves, I get a Br minus in solution. This is a halogen. A halogen, especially the bigger ones, is stable. It's big. It can stabilize the charge. It can carry it well. If I have something with resonance, let's say my leaving group is an acetate, something like that. Not something you're used to seeing, but it can absolutely happen. If I kick this out, oh, you know what? Let me show you one that you're more used to seeing. If you have learned about turning alcohol into a good leaving group, one of the molecules you will have seen is a tosylate. So we put an OTS to make alcohol into a good leaving group. What you get when it leaves is an OTS minus, which, okay, why is that a good leaving group? Well, let's see. OTS, tosylate, let me draw it out, is a toluene sulfonyl, and it's got the O. That O from the alcohol is right there. The reason this is such a good leaving group is oxygen is not carrying the burden of charge alone. It can resonate here. It can resonate here. That is what makes it stable. But if I take the alcohol and I don't turn it into a good leaving group, then what I'm creating, what I kick out is an OH minus. And this right here is my sun in the morning. So my husband takes him to school most of the time, and he'll stand at the door and he'll give me a hug and a kiss, and I'll start walking to the car. Leaving group, right? He leaves the house. No, that kid does not walk to the car. He will turn around, knock on the door, bang on the door, scream, "Mommy, last one huggy. Last one huggy." He wants another hug before he goes. "I give you another one, another hug and a kiss." And I'll give me a hug and a kiss. And then he'll leave again. But he's not a good leaving group. He comes back, "Last one more, to the point where we have to tell him, "Okay, I love you, kid, but like, you got to get out of here. You got to go to school. You're not being a good leaving group." OH minus is unstable. It is very strong. It is very charged. It is very, very reactive. You try to form an OH minus in a solution with a carbocation, that thing is going to turn around faster than my son, who realizes he needs one last one hug. And so it's not a good leaving group because it does not stay gone. But if, and I seem to have run out of room here, so let's see if we can squeeze it in. But if I take that same water molecule and I bribe it, option 1 is an OTS. Option 2 is if I take that OH, I protonate it like I showed you in the reaction higher up on this page, like this. Now, when it leaves, what I'm left with is a water molecule. A water molecule is neutral. This is stable. This is a good leaving group. This is definitely not my son on the way out the door, because this thing is happy to go. So that is a good leaving group because it is stable, and therefore it does not come back in desperation because it needs another last one huggy. Brianna, that was a very good question. I'm glad you recognized that even though you have the information, you have to memorize it, and that is not acceptable. So let me know if that clarifies it for you. Question, but isn't O a good electron donating group since it's quite... I don't know when you typed that question, so I don't understand the context. Can you please explain? And that way I'll be able to go back. Can you explain again what the H2SO4 does in an SN1 E1 reaction with a good leaving group? Yes, it is simply a source of protons in solution. And so in this case, it's how we bribe the alcohol. Alcohol does not want to leave. Sometimes we'll bribe my son and we'll say, you can have a toy in the car, or you can have, well, we don't give him food in the car, but every now and then if we're desperate, we'll give him a snack in the car because that child loves to eat. If you go to the car, you can have a toy. And now he's happy to go to the car because it's no longer a bad leaving group. It is now a good leaving group. With an SN1 reaction, it's more about just making the entire solution positive. Therefore, the carbocations are more stable in that solution. Do you always protonate when you have a bad leaving group? So the only leaving groups, the bad leaving groups you would have learned this in this chapter would have been your OH, alcohol, or maybe an OCH3 or an ORCH3 being an example. In this case, protonation is your best option. I think protonation is the only thing you would have learned here. But for this one, you would have learned any of the following, depending on your professor. You can use H+ like H2SO4. You can use SOCl2. You can use atosyl chloride. It's written also as OTS Cl. Let's see, PBr3. I want to say these are the most common ones you would have learned. I can't think off the top of my head if there's another one. So these are probably the top ones. Let me know if that answers your question. These are all different ways to bribe it, but this one, because it's got the OCH3 there, it's a little bit different. And so the H+ is typically what you're going to use. All right, the one you've all been waiting for. Let's take a look at what happens when I react this molecule here. And I think this may even be on the midterm, this or something like this. I don't remember exactly what I put. Just put midterm in the comments and I'll send you a copy. If we react this with H2SO4 and H2O. All right, so first we'll try the shortcut. And the shortcut is, cross out the leaving group. Well, first let's see what we have. H2SO4 is a source of H+ in solution. H2O is my solvent. I'm given nothing else, so I know it's going to be a solvolysis reaction. Solvolysis is slow. It is weak. It'll do an SN1 or an E1. I know I'm going to lose my leaving group and ultimately get a carbocation here. But I can't simply take my shortcut as I did before, where I redraw the molecule as I started. And then, so for the shortcut, it's for SN1, you redraw it as you start, and then you put your alcohol for the substitution, or you put a pi bond for elimination. And the reason this does not work is this problem right here. I have a secondary carbocation forming near a tertiary carbon, which would absolutely and immediately give me a hydride shift in a typical situation. But what I have here is an even more important rearrangement, and that is what I have in that tertiary situation. If I have a secondary carbocation near a 5 or 4-membered ring, a 4 or 5 carbon ring, then I will have a ring expansion. That ring is going to take the opportunity to get more stable, to get bigger. And so what I have here, let's take a look at the mechanism so we can see, is as follows. Where did it go? I don't know why it went all the way up there. Let's go to the new page. Let's do the mechanism here step by step. The first thing that's going to happen in this reaction, the chlorine will leave, giving me a carbocation intermediate at the secondary position. This is where all the trouble begins. I can either do a hydride shift from the tertiary position, or I can recognize ring expansion. Ring expansion is going to be these right here. The whole thing shifts over. I like to redraw it exactly as I see it because it helps to visualize what moved, which bonds went where. So I used to have a bond right over here. Now I have a new bond right over here, like that. I kind of missed. Let's try that again. A new bond right here. And because this carbon lost a bond and got nothing in return, that is where my carbocation is now. So I have this thing right here. It is a little bit of a mess. So for the next step, I like to just redraw it. I'm not doing anything different. I'm going to number it first. 1, 2, 3, 4, 5, 6. That allows me to redraw it without even having to look at it. Pretend you can't see that. I redraw a 6-membered ring like that. And then let me number it so I can put everything where it needs to be. On carbon 1, let's take a look. I have a methyl group, so I'll add it right here. On carbon 6, I have a carbocation right there. The bond used to be between 2 and 6. It used to be right there, but it's not. And now, well, let's not forget the old rule. A carbocation on a secondary carbon near a tertiary carbon, hydride shift. So I will have another rearrangement to give me the most stable substituted carbocation right here. Now I have a stable carbocation. Now I can jump in for the final step. And for the final step, I have two options. I can have a water molecule that comes in and attacks directly at that carbocation position. Let's put this product down here. What this will give me is, well, not quite the final product. What I have here is an OHH, 1 lone pair positive charge. We want to deprotonate it though. So I bring in a water molecule, grab the proton, give it back the electrons, and there's product number 1. You know what? Let's draw it here so we can draw them side by side. We'll put it like this. There is product number 1 with an alcohol sitting at a completely unrelated position compared to what we started with over here, because the molecule completely changed. Option number 2 is if that water molecule comes in, but instead of attacking at the carbocation, it attacks one of the beta hydrogens, which in this case, it doesn't matter because the molecule is symmetrical right down the middle. And if it grabs a beta hydrogen, giving the electrons back, what we get is a different product right here. with a pi bond between the alpha and the beta, giving me both the SN1 product and the E1 product, looking nothing like that starting molecule. And there's a couple more like this on the midterm, so make sure you comment midterm and download so you can practice. How do you distinguish between SN1 and SN2? Very good question. With SN1, you have a weak nucleophile. Where did I put the SN1 notes? Right here. Carbocation is a slow step. Absolutely no carbocation in SN2. If you have a strong attacker, that strong attacker is going to attack before that slow carbocation can form. If you don't have a strong attacker, meaning an OH minus, an N minus, a C minus, something really negative and aggressive. If you don't have that, then you go the slow route. Luna, yes, email me. All right, so this was just one piece of the puzzle. Make sure you go back to last week's session, which is linked in the description.